All right, guys, we'll get started here in just a few minutes. I am going to record this one, so we're going to be able to put this up on YouTube and whatnot for the folks who couldn't be here. We have some folks in Europe and whatnot, and potentially also in Australia who were wanting to go to this, but we're not able because of the time that it is for their time zone. So we're going to record it and share it with them so that they can watch it at their convenience. So that'll be good. Now, the only change that we're really making to the class for this second session is I did add one case study back in. For some of you, it'll be kind of, maybe a bit of a laugh just because it's something that's probably pretty common if you've worked on this particular breed of vehicle. It's a diesel case study. So most of the case studies that we're going to talk about in here are not, I don't want to call them overly simple. But it's really more about the central theme of the class. That's really what I want you guys to get out of it. It's not necessarily, we're not trying to get into the nuts and the bolts of the diagnostic too detailed. It's mostly talking about, the concept that we're talking about, mindset, the overall picture of the diagnostic, things of that nature. So that's really what I want you to take away from this as we go through things here. So we'll get started in just a couple of minutes here. Actually going to reach up and turn the fan on in this room. Yeah, I'm not real surprised. That's a lot of the folks that I see at a lot of other training events either, right, Adrian? It's it's good to see that there's a lot of people who go to training regularly and value what they can do. I think that's nice, and ultimately, it's for everyone's benefit to go to as much training as possible. And really, for this class, I'm doing this as I want to do it. I want to practice. I want to get better. I'm going to be doing a lot more training, as a matter of fact. Coming up in the near future here, I actually got hired to work for TopDon. So I will be working for TopDon as their director of training. So I will be building classes for major training events, presenting those classes. I will also be highly involved in the beta testing part of the organization. So that'll be good. I'm going to be able to continue doing my mobile diagnostic and that kind of stuff as well. So that's great. I appreciate all the congratulations from you folks. It's definitely a big deal, and I'm really excited about it. So super excited to see more of you at some of the major training events. I've got a lot of classes to build in a very short period of time. So it's going to be it's going to be a big deal. That's for sure. It's it's a little bit, a little bit nerve-wracking just because it's all at once, and I'm going to have a ton of work to do in a pretty short period of time to get ready for some of these shows that we're doing. So, very excited, but I like to do these classes because it's great practice for me. And, I've done a lot of presentations over my lifetime and whatnot. I did actually go to college, and I have a degree in communication. So I spent a lot of time doing presentations, writing speeches, things of that nature. So definitely, I'm not unfamiliar with a lot of this practice of giving classes or teaching or, things like that. But I haven't built a ton of classes from the ground up. So it's really nice to be able to, do this for everyone's benefit. If you haven't seen the, Adrian, nice. Well, it's good to have that degree. If you've got one in electrical engineering, that's about as helpful of a degree as you could possibly have. Mine's good for certain things, when I've worked in the shop, in the front shop side of things, or when I was a service manager, communication degree was helpful for written communication with customers, documenting work orders, things of that nature. But, a little bit less so on the technical side. It didn't really help me at all with diagnosing cars or anything of that nature. Jeremy, yeah. Definitely, there's definitely some benefits to having the degree. Mostly just, I don't typically get burned on grammar or spelling most of the time. So if you do find any grammar or spelling errors in my presentation, tell me, because I'll be extremely embarrassed by that. But otherwise, it's been a degree that's been helpful in certain aspects. So looking forward to using it and building some of the classes and doing some more stuff in the future. Now, as we get started here, I just wanted to say, I'm doing this as a benefit also to benefit an individual who's actually in the training tonight, Mr. Kindred. He is actually recovering from cancer, if I'm not mistaken, and there is a link to his GoFundMe on the page on Facebook. So if you're willing to do any donations to help him out some, I would appreciate that, and I'm sure he would as well. So, I wanted to do this class as a benefit to try and help him out. But, again, I want to try and help everybody I can learn, improve. I think it's beneficial every time we get an opportunity to hear how anybody goes about a problem, regardless of what level they're at, whether they're, the John Thornton of the world or they're down here like me. It doesn't matter. As we get to listen and interact with other people and watch how they process a problem or think about a problem, you learn something from that, and it changes the way that you look at a problem in the future. So that's really the heart of what I hope to give you from this class at the end of the day. So we'll go ahead and get started. Periodically, I will have to pause for a moment just because I have to admit people to the meeting. So if you hear me pause unexpectedly, that's because there's still a few people joining. So we're going to go ahead and get started. Now you'll notice on my first page here, the theme is a German flag. A lot of my case studies are European vehicles, which, if you're a European guy, a lot of these are going to be pretty predictable for you as far as what the outcomes are. But I did use some domestic vehicles here and there as well. So we'll go ahead and get started. So Shotgun Diagnostics is my mobile diagnostic thing that I do. I was doing it on the side when I was working for Garage Gurus, just kind of a after hours thing or on the weekends to pick up some good case studies and to continue sharpening and improving my skills. So I did it mostly just for, those purposes. I always thought it was something that I could refine and improve over time. And so I've continued to do that. And of course, I go to as many trainings as I can afford to and whatnot. So continuing to try and learn and get better. So anyway, this is basically what I want you to get out of the class. Think about what goes into a fault code. We're going to talk about kind of the logic process or the background behind what each control module looks at as far as various data it has both programmed internally as well as inputs that it's measuring that allow it to determine when a fault is physically triggered. So we're going to talk about that and go into that to an extent. We're not going to get super deep or super technical, but I think it's important to understand some of that because it's also important to realize what the limitations might be as far as that goes. Also going to talk about just our approach. How do we deal with fault codes? What are we looking at as far as data input? What are we using the fault codes themselves as a gospel or Bible or whatever you want to call it, or are we taking them more as a clue? Are we thinking about them as just a footprint in the snow, just another thing? If you're being like a detective, you want to look at fault codes in that respect rather than look at them like many of us love to deride and make fun of the folks at the parts stores. They like to use fault codes as a silver bullet, right? They like to say, hey, replace this part because you got this code. And if you've had any experience with any diagnostics at all, regardless of the level you're at, you've learned that that is oftentimes not the case. Regardless of what the code is, it could be caused by that specific part that's called out in the physical fault code definition, or it might be something completely unrelated. I guess not technically completely unrelated, but you get my point. A couple other things you want to look at. When we have situations with no fault codes, it's important to remember that sometimes, and we'll go in when we talk about the logic of fault codes triggering, it's important to realize that control modules sometimes will not trigger a fault code when we would expect them to. So specifically situations where you can even look at the fault code definition and it says, hey, this car is broken in this specific way. We should have a fault code here, and yet somehow we don't. And I'll actually give an example that's not written in the case studies that I'm presenting, but I experienced actually just last week. So the other situation I'm sure you've probably come across, and if you haven't yet, I guarantee you will, situations where a fault code is not deciphered correctly by a scan tool. Maybe the scan tool gives you gibberish. Maybe it says no definition found. Who knows what it's going to say? But the point being is that sometimes we're not going to get any useful data, even if there is a fault code tripped. There's also situations where the OEM does not provide any information on a fault code. European being the best example of that. Many situations, there's a definition at best. Sometimes there's no definition. Maybe your scan tool is the only definition you have, and service info has nothing. Now, I would like to preface that on European vehicles, if you don't spend a lot of time on them, the reason why you generally don't find a lot of fault code information on European vehicles is the manufacturer builds this information into the factory scan tool platform. So if we're dealing with a Volkswagen Audi, Otis would have that information built into a guided fault finding test plan. If we're dealing with BMW, ISTA-D, which is their diagnostic platform, would have that diagnostic information in the physical platform of the scan tool. So it's important to keep that in mind, just because if you are starting to get into European cars, or maybe you work on them every day, when I worked at Identifix, we'd get a lot of folks who would be upset and frustrated because there was no information available on a given fault code in the service information. And this is not something that's the fault of Identifix, ALLDATA, or Mitchell. It's just something that is not physically published in the service data. So just one thing I wanted to mention. So this is a model that kind of shows you some of the overall process and information that you're going to see related to what's going into the logic behind how a control module controls things, evaluates things, etc. So we can see there's a lot of different things here. We've got, measured variables, we've got analytical knowledge, we've got heuristic knowledge. So these are all different types of data that can be programmed in as parameters into a control unit in order for it to evaluate and determine whether or not there is a fault. So don't get hung up on this. It's not crucial to really get into this level of detail in order for you to be successful in your diagnostic process. But I think the more that you learn about it and get familiar with it, the more you'll be able to not get sidetracked by a fault code or confused or misled. So this is the way I like to look at it. So I kind of redraw essentially what was communicated in the last slide in maybe a little bit more simplistic terms. So what does the fault code logic really look like? What is the control unit physically measuring, looking at, checking values of, etc.? So we've got on the far left here, we got signal analysis of directly measured variables. So that would be things like cam and a crank segment. Are they where they're supposed to be, when they're supposed to be there? It's physically measuring the signal via the sensors, and that's how it's determining whether or not the cam and the crank are in sync, right? So that's a signal analysis. Then we've got limit value checking. Limit value checking would be something like a plausibility fault. So that would be something where when you turn key on engine off on a lot of cars, the throttle will sweep from closed to open and back. The ECM in that particular situation is looking to make sure that when that throttle blade closes all the way and opens all the way, that the values that the ECM is seeing meet a certain level of threshold, right? So it has programmed limits for that. And if it doesn't see it meeting those values, it's going to put the vehicle into limp mode. Now, a lot of that happens in situations as a result of things that we've seen with like Toyota, where they had uncontrolled acceleration and things of that nature. This is much more of a safety-related feature now. But that's not the only system you're going to see that on. There's plausibility-type faults for a lot of stuff where they're looking at, absolute values, circuit high, circuit low, voltage ranges, things of that nature. That's limit value checking. And we've got process analysis. So process analysis is where they're using a mathematical model to determine whether or not something is matching up with what it should. So that would be airflow. So how does the engine know how much airflow is actually supposed to be going through the throttle blade and being the map sensor? What is the map sensor reading, or what is the mass airflow sensor reading? Well, that's a function of the position of the throttle blade, right? So the computer has to be programmed to know how much airflow it should be expecting based on the position of the throttle blade. So that's a mathematical model that is physically programmed into the control unit. and it's using that mathematical formula to derive, hey, we know there's a problem because the throttle blade's at 30%, and my map sensor is reading too high or too low. So we know something's wrong there because the model that's mathematically programmed says that I should have this value, and I do not have that value. Now, the computer uses a lot of these methods in some various combinations to monitor various systems as a whole. We've also got one other thing. So the other thing would be qualitative information that can be programmed in. So you might ask yourself, what does that mean? So that's more like experience-based data. So think, for example, on a radar system on a vehicle. A lot of vehicles now have a radar sensor on the front grille for emergency braking and things of that nature. When you're dealing with that, the radar sensors are programmed to have, they'll set an obstruction fault, or it'll deactivate the system after the sensor is blocked for a certain period of time. Now, how does it know how long it needs to go before it sets that? Well, they did testing in a lab, and they did experiential testing to find out, okay, how long should the radar sensor be blocked before we deem that as not an obstruction that's an obstacle, but instead an obstruction that is something that's permanent, right? Or something that's ongoing, like ice or snow blocking the radar signal. So that's something that's experiential data that gets programmed into the control unit so that it knows how to deactivate a system or control something like a radar sensor's function or override capabilities. That's how it knows how to do that. So again, control units can use any or all of these in some combination to monitor various systems, and they're going to use them depending on the application, what it's trying to physically accomplish. It's going to use one or more of these means to do that. So I think it's good to think about this, because then you can ask yourself, what's the nature of the fault that you're dealing with? So this is just another example. This is obviously focused around Ecm logic. So here you can kind of see that they divide it up into compartmental sections. So we have like combustion process, we have catalyst, and then we have cooling. And so you can see there's inputs and outputs related to all of those that the ECM kind of looks at to determine, okay, is everything working correctly, right? So throttle blade, injection, ignition, all of these things. Again, you don't need to know what all the specific symbols are, but just it's important to know that there's a lot of inputs and outputs involved in the overall control structure. I think this is really helpful when you're attacking a problem to think about something and break it down into a system of inputs and outputs, because then you can determine whether or not you have an input issue or you have an output issue. Is it something that's being measured on the input side that's causing a faulty process to take place? Or is it all the input data is there, but the output control is not happening correctly? And a throttle blade is obviously the best example of that, right? So we have the input would be the APP sensors. How much are you trying to command the throttle? The output command is the throttle actuator motor, and the feedback reading is the throttle position sensor itself. So it's kind of nice to think about it. I think the throttle is the easiest section to kind of think about in your mind as a inputs and outputs model. Now, this is a little bit more detailed version where they break it down into subsections to a greater degree, but it's kind of nice because you can kind of visualize for yourself what individual section the control module is breaking down a subsystem into. So you can kind of figure out, okay, I'm dealing with the camshaft, that's viewed as part of the intake system. Now, all of these pictures come from a book that is, and I forget what the author's name is now, but it's a Bosch book, essentially. Combustion Engine Diagnosis is the name of the book. So all these images come from that. So if you want to look at it, it's a great book. There's a lot of math in there, most of which I don't understand or care to know. Engineers know. But it's not really practical for most of what we're doing. But it is helpful to look at some of these diagrams to process kind of what's going on internally within the control unit. So you can see throttle blade, tumble, those are all part of the intake system. And you can see that the fault detection is kind of the, hey, this is what's being evaluated and how long it's taking to evaluate those criteria. So we've also got fuel system. That's obviously a subsection we got. Ignition system is a subsection, and EGR is also a subsection. So again, not crucial you memorize any of this, but I find that it's a helpful thing to kind of visualize anytime you're attacking a problem, specifically more related to drivability, obviously here, but a lot of systems are broken down into compartments like this internal to the control unit. All right, so this was an example I wanted to kind of go over, just talking about a good example of how there can be differences in codes in terms of what specifically a control unit has available to trip for a fault. And it can vary between manufacturer, it can vary between year, it can even vary between model. It doesn't really make a difference as far as whose name is on the hood. You always want to dive in and look specifically at the service information if it's available. Now, if it's not available, well, then you're kind of at the mercy of whatever your scan tool gives you. And we'll get into some situations like that. But this is a good example because at this beginning, this early build for Volkswagen, which was the first engine in the sequence of the EA888 architecture, which is now commonly seen as the 1.8s and the 2.0s from 2009 forward to now, they've had multiple generations and revisions, but this was the very first platform they had. And when it came out, they had 3 different codes to capture various failure types for the cam sensor. Some of them related to the signal pattern, some of them related to voltage, and it could set specific codes depending on what the circumstance was that the ECM saw. If we go forward to, this is a 2017 model, I believe the CXBB was actually started in 16, if I'm not mistaken, but it's a later platform, but they only have one fault code. So this particular fault code essentially it's almost more like heavy-duty trucks. So heavy-duty trucks a lot of the time will have a primary fault code like this, and then they'll have a fault code index reference like an A, B, C type of stuff. You've seen that probably in some of I want to say like BCMs and whatnot. I've seen it. Ford has it on a lot of vehicles now where there's like a fault code sub-index. So in this particular case, Volkswagen isn't showing that there's a fault index per se, but your scan tool might provide that depending on what it is that you physically see. So tough to say if you'll get that information, but it's important to see here that we can have just one fault code and the specific failure could be any number of specific things. Now for me, this affects my testing process, right? Because if I have something like this where it's a fault code where it could be multiple things, what's the easiest way to determine what the fault is? Well, in my mind, a lab scope, right? Because you can hook up to the sensor, you can hook up to all 3 legs, because in this situation, it's a 3-leg Hall position sensor. So essentially what you're going to have is a power, a ground, and a signal. So we could hook up to all 3 of those simultaneously on our scope and see what the failure is that's actually occurring. And we get all that data all at once. You know, a lot of folks will go through and do tests like resistance checking of harnesses or load testing wires or any number of other stuff. I like to advocate for the scope in a lot of situations just because it gives you a lot more data. Once you get comfortable with the scope, you'll be able to get more information all at once, and the setup won't take you as long as it does as you're learning the scope. Now, when you're learning, yes, I understand that it's not necessarily the most efficient way to test things until you get comfortable with it. But once you get comfortable with it, it yields so much more information all in one shot. So maybe that's why I've gotten so scope heavy on a lot of problems I run into, because of the fact that there are more fault codes I see like this where it's vague, right? It doesn't give us a clear direction of what we would expect the failure type to be. So we're going to go to a case study now. This one is a 2012 Land Rover. So this one was a drivability concern. If you're in a lot of the Facebook groups, I think I might have shared some of this information before, maybe talked about what the failure was already. But this shop called me and asked me for some help. They had replaced some parts, didn't have any effect on it. It was still running poorly, didn't have any power. So this was the initial scan. It had a bunch of misfire codes, including a random misfire. You see that P0316. Anyone who's a Ford person probably recognizes that as a very Ford-centric code. They love to trip that, and that's no coincidence. This 5-liter engine that's in this Land Rover is a Ford engine. It has been modified on the older Land Rovers like this 2012. It was direct injection. If I'm not mistaken, the Ford models back then were still manifold injection. The later 5 liters on Ford are now direct injection, but Land Rover had direct injection first. We've also got a couple of fuel pressure related faults. So we got fuel pressure rail system too low and engine cranking fuel pressure too low. So I like to ask, what kind of clues are the codes giving us? Well, we know the engine's running like crap, right? We know that we've got misfires, and we're pretty sure we have a fuel-related problem in some way, shape, or form. The shop had installed a rail pressure sensor and some spark plugs because they thought that the misfire was a problem. They said that the low side had verified as good pressure, so we didn't have any suspicion of the in-tank pump being a problem. That was able to generate full pressure as to spec. Volume was not a problem. So they were kind of out of, well, let's be honest, guesses at this point in time. They had tried a few things and didn't really have any success, and unfortunate for them, but that's why they called me to help them. So what I wanted to do first was go in and look at, okay, I was pretty sure I knew how the system worked, but I wanted to double check. So I went in and I looked at, how does this vehicle generate high pressure fuel? In this particular circumstance, this vehicle has a high pressure rail, and the high pressure rail has two high pressure pumps, one that feeds each bank of cylinders, and it is, you can see, down mounted on the side of the block. So that's a clue to us that it's definitely not getting driven off of the camshafts up on the top of the engine, because this is a quad cam motor, quad overhead cams. So basically not being driven off of those, and that is common. A lot of vehicles will drive them off the intake camshaft or the exhaust camshaft, not off an auxiliary camshaft, but it is an auxiliary camshaft on this vehicle. So I wanted to look a little bit deeper. So service information actually on these Land Rovers isn't too bad. They actually give you some good pictures and some good detail. We can see that the high pressure pump has got a flat tap at Fowler. We can see that the two pumps are being driven off this auxiliary camshaft, which is also driven off an auxiliary chain off of the crankshaft. So go a little bit further. Now this is a little bit low resolution, but you can see that the lobes on that auxiliary camshaft are offset. And that tells us that this particular camshaft, those pumps have to be timed specifically in order to properly build high pressure fuel. Now, this particular camshaft doesn't have any kind of sensor connected to it, so the engine control module has only one thing it can do. It has to assume that the timing for this is correct at all times. So when it fires the injectors and does everything else related to opening and closing of the solenoids on those high pressure pumps, everything is done based on the assumption that this is timed correctly at all times, which, if the engine's in normal functioning condition is true. So I asked myself, would a timing issue affect combustion? Well, yes, it would. You're going to have issues with combustion if you've got a timing problem. It can vary, depending on the nature of how bad the timing is off. It can also affect multiple things if you've got a timing issue and the high pressure pump is not being driven correctly. Timing on the primary chains. Now, if we've got an issue on the primary chain, is it also a reasonable possibility that the lower chain is also stretched and jumped? Usually, chain stretch happens as a result of poor maintenance, infrequent maintenance, inferior oil choice, poor quality oil filters, any number of things like that. A lot of the time I like to take a bore scope and stick a camera down inside the valve cover if it's easy to get inside there and just take a peek around. I've got one that's got a camera that points straight down and one that points 90 degrees. And you can see inside there a lot of the time and see if there's sludge or junk or other crap built up. And that can be a really helpful clue to kind of determine, all right, well, how well has this thing actually been maintained, right? And if it hasn't been maintained particularly well, we know that there's a lot more risk that there's going to be some more problems, with the vehicle overall. Timing of the high pressure fuel pump camshaft, that could easily jump if the primary chain has also jumped. And we know that that's going to cause an issue with rail pressure, right? Because we know that those lobes are offset and they have to be timed correctly. So what did I do? I went straight to looking at the timing. Now, I can't determine if the high pressure pumps are timed correctly off of primary timing chain, but these particular engines are known for timing chain issues. And as a matter of fact, this waveform was provided by one of the people in the class, Adrian. He was kind enough to scope. Now, this vehicle has 4 cam sensors and a crank sensor, and he scoped the intake camshafts and the exhaust camshafts versus the crank, as well as he scoped them individually or in combination. So he had 2 intakes together and 2 exhausts together. And he had the proper phasing set up and whatnot. Now, I like to be efficient and I like to be pragmatic when I'm doing a diagnostic. I don't always go straight to cam and crank. If the crank is a pain in the ass to reach, Or if the crank is, I got to backpin the ECM, or it's jammed down somewhere I can't reach, or I got to pierce a wire somewhere I'm not real happy about. Sometimes I'll just go straight to the cam sensors, because if the cams aren't in phase with each other, who cares? We know that it's out of time. It doesn't matter if it's in phase with the crankshaft if they're not in phase with each other, right? And since I had a waveform that provided me that information, I was able to do exactly that. So I looked at the intake camshafts. You can clearly see that the timing is not correct on the intake camshafts. So I told the shop, well, first thing I would do is warn this customer it's going to get real expensive real fast. Second thing I would do is do some further investigation. So we know that the primary chains are out of time. We know that checking the pressure or the timing for the high pressure fuel pump camshaft would probably be a good next step, right? We want to see if that chain is also stretched. The probability is reasonably high that that's the case. If nothing else, we know that the vehicle is going to have trouble properly timing injection events if it's reading off camshaft sensors and getting bad data based on the positioning of the camshafts. So no matter how you slice it, we've got a cascade problem here that's could be much more compound than just a primary chain, some guides, phasers, etc. Now, we know that there's also some other possibilities related to the high pressure fuel failure. There could be a damaged auxiliary camshaft lobe or camshaft. You could pull the pumps out. You could look at the lobes with a borescope. We could look at the high pressure pumps themselves, examine them. They can grenade and shoot metal into the fuel system. That is possible. More common on common rail diesel, I'm sure. If you've worked on any common rail diesel, you've probably run across that. But it can happen on gasoline vehicles as well. You can also get the flat tappet follower can get damaged as well. It's real common on some Volkswagen models, which is why a lot of them have switched over to like a roller style follower instead. But those are some other possibilities. So these are just some things that I like to tell people anytime you're dealing with timing chain related faults. As a matter of fact, there was actually a post in one of the groups today on, I believe it was a Hyundai, and they had some rattling and noise, which was presumably coming from the phasers or the chain at idle. And flat out, like the first thing you need to do if you've got chain stretch is you need to check base oil pressure when the engine's hot. Now, if the engine doesn't run, then you probably need to warn the customer in advance that doing the chains may or may not fix the vehicle, and they could be in it for an engine plus whatever it takes to do the chains. That is a major risk. And, you know, Volkswagen, Audi, it's not uncommon that those will jump time and they will no longer run. And then you can't verify base oil pressure, which obviously makes things all that much more complicated because then you can't give the customer a comprehensive picture of the engine health. Now, in those particular situations, if you run into that and the vehicle is not running, that's when I would even advocate further for something like dropping the oil sump, looking in the pan, looking for debris, sludge, etc. When you discover things like that, I even had one of my friends actually sent me a picture of a 2-liter Land Rover, which is actually a Ford engine, again, that had a bunch of sand and dirt and junk in the bottom of the oil pan. And of course, you know, there was some issues with oil pressure on the engine. And it was no surprise, right? Because you could see the signs that the vehicle has been poorly maintained and caused some major damage to the engine. So I always recommend checking hot oil pressure when the vehicle's idling. Make sure it is above spec. Most of the specifications on a lot of these VVT-related engines, the specs are too low. If you've worked on a 5.4 Ford, you'll know that the Ford spec is written way too low for what it really takes to drive those camshafts correctly. So, of course, if we have any kind of major debris or junk in the engine, you know, it's been poorly maintained, there's sludge, dirt, sand, all of that gets circulated through the engine and polishes clearances over time. And of course, if you've had any metal that's broken off and gone through the system, like chain chunks or, you know, anything like that, it's going to polish those clearances and you're going to have a pressure drop, which is going to create more issues. And the VVT will probably never work correctly again unless you do a full engine rebuild. So I always recommend assessing all system health and integrity, and of course, looking at the service history to find out if there's any complicating factors that you might not be aware of right out of the gate. So what did it end up being? So after the testing we did, and the shop did check the high pressure timing, high pressure pump camshaft timing. It was out of time. So they did end up selling both upper and lower chain. They did retime everything, and the vehicle was fixed after that. So I just like to point out in this particular situation, the vehicle was out of time, but there were no timing related faults. Now, many of you have probably run into situations where if there's a misfire fault, you'll notice that other codes that you would expect to be set may not have tripped. And that is absolutely true. Misfires can disable the criteria for setting other fault codes, such as timing or other things. So it is important to remember that sometimes if a specific code sets, it might disable the ability to set another fault code. Now, I've also had situations where no code's set, even though there's a clear problem with the engine. So just be aware of that. Don't stand on the principle that, hey, it should set this code, but it's not, so it can't be that. Don't use that as a criteria for exclusion. So what about a situation where we have a fault code that's vague? Maybe it has poor detail or no detail at all. Maybe the OEM service information has almost nothing. Maybe it's a definition and nothing else. Or maybe you have no information whatsoever. Common if you're dealing with Porsche, for instance, and you don't have the factory website. So this would be an example of a fault code that's pretty vague. Now, if you think back a little bit to what we were talking about in the ECM modeling and the mathematical models, you can imagine that this is a code that is based off of some mathematical modeling. So we've got a manifold absolute pressure to throttle angle too low. So the vehicle isn't happy about what the manifold pressure is based on the position of the throttle blade. Now, this particular fault code is notorious on a lot of BMW, or there's some similar fault codes like this that are notorious on BMW for being tripping and people having issues finding the root cause. Now, I actually dealt with a vehicle, and I did not write it up as a full case study. Of course, you know, those situations where you get an awesome case study that you could have done and you forgot to document it, you kick yourself for after the fact. But did have a vehicle like this that was setting this specific fault code, and it was camshaft timing that was off. The camshaft timing was off. As you can imagine, the amount of air that the engine is moving is going to be different than what it's expecting to be moving, and that is a function of the camshaft timing. But it did not set any timing faults. Now, I do not believe that I noticed anything in the description here talking about disabling camshaft timing related faults from setting if this particular fault code sets. So they're not telling us that that code shouldn't be setting. But again, it's important to remember and ask ourselves, what are the possible causes? Now, BMW Mini gives us a little bit of information in this action and service section here, but it's kind of vague, right? It's not real detailed. So what we need to do is remind ourselves, how does the system work? What is the overall function that's being evaluated here, and what are the plausible explanations for that? So in doing that, I like to look at, okay, if there is fault setting criteria, let's figure out what it is. So the threshold for when the fault's going to trip, voltage at this level or that level, map sensor reading versus throttle blade of this or that, whatever it might be. Service history on the vehicle, because a lot of the time you'll find things that explain everything that were recently touched, either by a DIY, another shop that maybe isn't familiar or comfortable with the vehicle, or maybe is not really trained and shouldn't be working on it. I mean, there's any number of situations there that it could be explained by the previous service history. The other thing I like to do is the functional system chart. So what I'm talking about here is this. Draw yourself up a system chart like this. Now, this isn't meant to be comprehensive, and I'm not trying to kill every bird with this particular stone. You obviously could go into greater level of depth depending on the vehicle and get more detailed on this type of thing. But I think it's really helpful to make something like this for yourself. Draw it up. Ask yourself the question, if we've got an air mass plausibility, the amount of air being moved through the throttle blade is not matching what it's expecting, well, what are the different things that could be happening that could cause that, right? So like we talked about, camshaft timing, we could have variable valve lift issues, we could have anything that affects the ingestion of air by that engine. So we could have leaks in the intake piping, turbo piping, we could have issues with the throttle valve itself, we could have one-way check valves, we can have PCV system issue, we can have low compression. I mean, there's any number of things, right? But if you draw something like this up for yourself, you can knock each one of these off and chop the branches on this tree off one at a time, and then you can hold yourself accountable so you don't ignore something that you shouldn't, and you don't miss something that is a fundamental reality of how the engine works, right? Because all internal combustion engines still operate on the same basic principles. How they accomplish that goal might vary from engine to engine a little bit. BMW uses Valvetronic, other vehicles don't, except for obviously the new Toyota that has that BMW motor. But anyway, the point being is the way they accomplish it might be a little bit different, but the goal is still the same, right? They're still trying to move a certain amount of air for the combustion process. That's a metered amount of air. It's supposed to be X. Is it X or not? And then you ask yourself, what is broken? What is causing it to ingest more or less air than it is anticipating? So I think these charts are really helpful to draw for yourself. If you are interested in this program I use to make these, it's called Simple Mind, and it's a really, really, really cool program. You can create some really nice links, things of that nature. You can actually hot link to like Google Drive stuff. So if you want to build this out into a really nice tree for yourself with a ton of detail and whatnot, you certainly can. It's actually pretty awesome. So takeaways from the case. Studying and understanding how the system works, right? This is the biggest thing you can do for yourself on anything. If you don't have service information, you're going to be at the mercy of your own brain and your eyes. That's really all you're going to have. But if you have service information, or if you have a network of people you can ask, so if you know someone who's really knowledgeable on the car you're working on, don't be afraid to reach out. So you got a friend who's good on BMW. Ask your friend on BMW, hey, I got this fault, air mass plausibility. What has it been in your experience, and where should I test first? That's one value of something like Identifix, right? And I'm not saying that you should ever look at things like a silver bullet, but it can help you be more efficient on where you should test first. Testing is still going to be what's driving your outcomes, not guessing. Brainstorming that tree of possibilities, that's really going to help you out. Drawing up a map like that on any vehicle you're working on, a specific subsystem, and asking yourself, you got a problem with a vehicle not starting? Well, draw yourself a chart. Ask yourself, what does it take for this vehicle to start? Does it have permission to start? Does it have fuel? Does it have spark? Does it have compression, etc.? And then also reminding yourself that the presence or the absence of a specific code doesn't guarantee you anything. So just because it doesn't have a timing fault doesn't mean it's not timing. And just because it does have a timing fault doesn't necessarily mean it's what you think it is. Now, usually when it has a timing fault, it is timing. I will say that. But I've had plenty of cars where it didn't set a timing fault, and it was timing. So this is a good case study. This was actually shared in one of our Facebook groups, and I helped a gentleman on it, and I asked him if I could use it for the class. I felt it was a really good example that was really just great on illustrating some of the code issues you can run into, both in terms of what information you get from the OEM, as well as really sticking to the symptom as opposed to worrying about the codes, right? So the symptom was crank no start. The fault codes, as you can see, P068A, U140A. Now, the definitions provided that by the scan tool, we had a power relay load circuit that's opening too early, and we got a terminal 30 open circuit. So not really a lot of detail in the definition there. Look to see if there was any information in the service info. Now, if you're familiar with Volkswagen Audi, as many European manufacturers, typically there's not a lot of info. That was definitely the case here. So there are what I like to refer to as cousin codes of the P068A code, and you can see they're all related to this ECM relay. And they give you some various information and criteria for, when each of these can be set. So you could use that to maybe ask yourself, well, do we think any of these criteria is being satisfied? Are we somewhere in this neighborhood that's causing this? Or are we just going to look somewhere else? Not really a lot of help here. Look on the P068A, again, Rostec. This is the Rostec wiki page I pulled this from. Got a little bit of information here. Not really anything super helpful. There is one thing at the bottom here that's a link to a TSB. The TSB, now you'll notice, is actually for not this year, though. It's a 2016 is the vehicle we're working on, and this is an 09 to 14. Now, the shop decided they were going to go ahead and do what the TSB said, which was to replace this relay, which is the primary engine control relay J271. Had no effect, as you probably could have anticipated. So he clarified the symptom with me, and he said that it was not firing on anything except cylinder 2 when it tried to start. So he had been suspicious that this might be something immobilizer related. So he swapped the ECM and programmed it and did all that stuff. He had another one around he was able to swap, and he said, nope, same symptom. So he did test the battery because, some of these European cars are extremely sensitive to voltage. I've seen that on a lot of Euro cars. I think it's actually becoming more common on a lot of cars, period. As the sophistication of electronics and load management continues to be more aggressive, you will see things, weird anomalies like this that could happen as a result of low battery voltage. Modules can lose configuration. Modules can get angry and drop off the bus. I mean, there's a lot of odd stuff that'll happen as a result of a bad battery, right? So he did load test the battery and it failed a load test and he did replace it, which, that's something you should do in any diagnostic process is test the battery with a load test. And when I say load test, I mean carbon pile load tester, not a handheld tester that's, just I can't remember, capacitance tester. None of those. That's not what you want. Those are great for finding smoking gun failed batteries, but absolutely not good for finding batteries that are marginal, and marginal batteries can still cause problems. He did also check the charging system and did not find any issues. So if we were going to focus on that relay, we'd probably be looking at wiring diagrams and trying to figure out, okay, why are we getting that fault code on the relay? So I probably would have hooked up a scope and looked at all the different legs of the relay to see what was happening, to see if any of that stuff on that fault code list for the relay had anything to do with what we were seeing. Spoiler alert, though, it wasn't anything related to the relay. So he did check some of this stuff, and he didn't find anything anomalous that he thought was odd. So he said, you know what? I'm going to go back and I'm going to scope cam and crank again, which is a good choice, right? We're dealing with something here where we're going to draw up the tree and we're going to ask ourselves what can cause a crank no start. Well, there's a lot of different issues. He already knocked off the immobilizer. He looked at it. He had permission to start. Everything checked out. Steering column lock open or unlocked like it was supposed to. Nothing there. Now, the anomaly he had was injection and ignition only happening on cylinder 2. So he goes back and he checks the timing. Excuse me. He did check cam and crank at the beginning of his diagnostic, and he said that he didn't see anything off the bat, and it was timed correctly. However, he decided, and I said, I think this is a good idea. He said, I might go back and recheck it one more time. And I said, I think that's a good idea. I think we should check it one more time. And maybe I said that because this engine is known for having so many issues with timing that I was not entirely trusting that it was timed correctly, or that something else maybe related was going on. So he rechecked it. Now, he did not send me the waveform, unfortunately, but he did find that the crank sensor signal was dropping out. It had some anomalous dropping sections on it that he was like, man, something's weird there. He looked in greater detail. Now, maybe he missed it on the first capture because he didn't have his time base set up correctly. Maybe his sampling was set too low. Who knows? That is one of the things you want to pay attention to when you're dealing with your scope. You want to make sure you get good data, robust and detailed data with your scope so you can then evaluate if you've got an anomaly. And there's been a lot of weird sensor issues that I have only caught with a scope by having the proper sampling rate and the proper time base and the level of detail necessary to catch glitches, right? So he did find that dropout. So he pulled the sensor and he found a damaged reluctor wheel. So this makes a lot more sense in hindsight now, right? Because if we've got firing only on one of 4 cylinders and we've got a dropping out pattern, what does the vehicle use to determine when it should be firing the coils? When is it used, or what is it used for determining injector timing and firing? Well, a combination of cam and crank. And if the signal is dropping out, well, we know the car is going to be having issues, right? So it makes all the sense in the world in hindsight. But it is something that we could have got by going back to our tree and asking ourselves if we were focusing only on the symptom. The fault codes were meaningless in this situation. They didn't really give us any clear direction or help us in our diagnostic, partially because the information provided by the OE was lacking, but also because, well, frankly, they didn't really explain what was going on, right? We didn't have any crank sensor signal faults, nothing, absolutely nothing related to that, despite the fact that we obviously had a crank sensor problem. So just another great example that illustrates the need to be following that symptom and not worrying about the fault codes in a lot of situations. If the fault code gives you a clear direction or it really gives you a good clue, great, focus on that. But if it's vague or it doesn't seem related or it doesn't really explain anything additional related to the symptom, don't worry about it. Worry about the symptom. The symptom will steer you to the answer for sure. You can be much more confident in that if you do that and follow the symptom. So this is another one I dealt with. So this is kind of an interesting one. Shop called me up and they said they had a 2016 Chevrolet Trax. Now, that's not that old of a vehicle. Now, I live in the northern states here, so there's a lot of corrosion, which is a bit of a hint as to what we're going to find with this one. But it was an interesting case, right? So this customer was a driver for like Amazon or something, and he did, or DoorDash or something. And apparently he drives for 8 to 12 hours a day. He said that the vehicle only stalls typically after driving it for somewhere between 8 to 12 hours. Now, the shop apparently was not really too worried about burning up their time, so they decided to take on a intermittent problem like this. Personally, for me, I don't think I would have said yes to this car unless the customer just wanted to leave it and let them run it in the bay with an exhaust hose on it and maybe a scope capturing stuff. Because really, in reality, you know, what are you going to do if you have no codes? And they said they thought they had one code in the BCM, and it never retripped after they cleared it. And anyhow, they had really no clues. So I said, well, what we need to do is figure out what it's losing, right? Is it losing voltage somewhere? Is it losing spark? Is it losing fuel? What's happening, right? So if we've got a stalling issue, I said, well, let's draw up a tree, right? What's likely here? Probably losing fuel or spark, right? That's most likely. It could be an electrical system fault, might be something weird like that. Not likely to be something compression related, not likely to be something breathing related, because it's so intermittent. I would expect it to be something more, typically with something mechanical like that, I would expect a more consistent failure and a less intermittent failure. Now, obviously, electrical could also be compound as part of the why are we losing fuel injection or fuel delivery? Why are we losing spark? It could be something electrical, right? Makes all the sense in the world. In fact, most likely it is something electrical. So I said, all right, let's find out what's going on. Now, they were screwing around with the vehicle, and they had possession of this thing for, at least a week. And they did finally determine they had, I believe they had an amp clamp on the fuel pump relay while they let it run in the bay, and they did actually catch it stalling, and they said that they lost amperage to the fuel pump. There was no power to the fuel pump. And I said, okay, well, you're losing fuel pressure. Okay, we know that the fuel pump lost all the power and shut off, so now we need to find out why. So they unfortunately did shotgun a bunch of parts at it. They put in a couple of fuse blocks, I think the front and the rear fuse block, and chased a bunch of things. And honestly, I was surprised that they got to the point that they did and then got so off track and threw a bunch of parts at it. But they did find that the run crank relay under the hood, which we'll see in the wiring diagram coming up here, was about 30 to 35 degrees warmer than all of the other fuses and relays in the fuse block. Now, if you're comfortable with electrical, and maybe you're not comfortable with electrical, but heat usually comes from resistance, right? If we have a buildup of heat somewhere in the fuse block, a relay, etc., we know that that's usually coming from something, either really high current flow or we have an issue with resistance. In reality, it really all goes back to resistance, right? So I said, let's look at that. Let's chase that. Let's see where we're going with this. So this was the diagram I think they should have looked at. So we could see the red line traces our power flow, and it goes all the way down, and then we go to the second diagram here, and it goes into this fuse block underhood. So KR73 here is the run crank relay. I don't know why it's called this here, but it was called the run crank relay. Anyhow, we can see that that feeds the fuel pump relay, and they had verified that the fuel pump was losing power. So we know that there's a problem here. We want to find out, is this relay not staying closed for some reason because the relay is faulty? Well, that seems unlikely because they had already replaced the entire relay fuse block with a new relay and a new everything, and no change. Still stalled. So this is the diagram that they really needed to see. And for whatever reason, now these guys have got all data and identifics, and this diagram, I believe, is on both sites, and they didn't find this relay for whatever reason. Now, I know a lot of folks like to look at these aftermarket redrawn diagrams. I don't. I think these diagrams are dangerous because they can be misleading. They can have incorrect information. Not that the OE can't, because I've been burned by that before too, but it is statistically more likely because this is a redrawn diagram. Now, in this particular diagram, it does actually contain incorrect information. You'll notice in this circle here, it says that this J233 splice is under the right kick panel. Keep that in the back of your mind. We're going to go back to this diagram. So what I told them to do was, they had actually also put an ignition switch in this. So we knew it wasn't the ignition switch by the fact that they had put a dealer ignition switch in it. So I said, all right, we're losing power down at the fuel pump. We know that it's dropping power on this KR73 ignition main relay on the underhood fuse block, right? So they said, all right. So I said, let's find out if we're losing power at the J8 terminal, which is the input side of the coil for the relay, or if we're losing it at the BCM. Are we losing a command? Are we losing voltage here? What's happening, right? So they did find out. They said they were losing power down at the main relay at the fuse block. So it was happening before the underhood fuse block. So I said, well, what about at the BCM? And they go, no, we did not lose power there. I said, okay, so you got a splice in between there. So we need to go look at the splice. So I said, all right, let's check that splice for damage. And of course, when I look up where the splice is located, it's in the driver's front in the kick panel area. Now, we noticed that aftermarket wiring diagram told us it was on the right side, which would be the passenger side. That's wrong. I said, look, it's on the driver's side. This guy's a delivery driver. He gets in and out of the car hundreds of times a day. We're in an area where there's corrosion, there's brine, there's salt, there's all sorts of crap on the ground getting tracked into the vehicle repeatedly. And I didn't see any floor mats in this vehicle when I went out to look at it. And I said, this has got to be what it is. So then the shop also checked the resistance across the terminals at the relay in the underhood fuse block, and they found 7 ohms of resistance. And I said, well, there we go. There's where your heat's coming from. Sure enough, they pull up the carpet and they find the J233 slice just disintegrates, just gone. But what is the key takeaway from this case? We had no fault codes whatsoever. All we had was one clue. We had one clue. It's stalling, and we have a heat differential on one relay. Just one thing. That's it. That's all we got. Oh, yes, we got a raised hand on this one. So, Travis, you can actually unmute yourself if you want to.
Sorry, that was by accident. I apologize.
Oh, no worries. All good. All good. All right, we'll proceed. So, anyway, what you get out of this is, if we drew up that tree for ourselves again about what can cause a stalling issue, and we followed the symptom, we can figure this case out, right? Now, again, I would not recommend taking on a car like this where it's only stalling once every 8 to 12 hours, because holy Lord, you are never going to make any money on that as a shop or as a mobile diagnostic person. I would say, hey, the customer wants to leave it with you and you can screw around with it when you're slow or whatever, fine, totally good there. But if you've got something like a picoscope and you can set up a long capture, you absolutely could set up a way to find out what was causing the stalling. What are you losing, right? So that is possible. I like a thermal imager, and I think it's an invaluable tool. I wish I had a capture from this one I could share. But a thermal imager is something that's a really, really good tool to take out anytime you got something weird, especially an intermittent, because weird electrical stuff, the thermal imager picks that stuff up like a sore thumb sometimes. Now, if it's a splice somewhere where it's under the carpet, you're probably not going to find it that way. Maybe you get lucky if it gets really hot, but otherwise, if it's something in the fuse block or whatever, you might at least get a clue. So it's good to take that thermal imager out for stuff like this, because you do find stuff that can really help you out. So this is another case I had. This one's really, really basic, but it's a great illustration of not getting scared away by a European vehicle, especially a European vehicle where service information is extremely hard to come by unless, A, you have all data, and all data does have a lot of Porsche information, but not really any fault code information most of the time, and B, not being scared away because of the name badge on the front, right? Because the system that we're looking at here, which is a blower motor not working, they can only work in so many ways. Every manufacturer is trying to accomplish the same task with the blower motor, right? Circulate air through the cabin. That's the job of the blower motor. There's only a handful of different ways that it can really accomplish that task. Now, don't get me wrong. I'm sure engineers will come up with new and weirder ways to do it eventually. But right now, in our experience, Generally speaking, there's a certain number of methods that they use to control a blower motor. So there's no OEM troubleshooting information on this code. I was helping a gentleman with this case on the Automotive Technician Mentorship Group, actually, as a matter of fact. He was very hung up on the fault code. He was very hung up on, I need to know what that fault code means. And I told him, no, you don't. You don't need to know anything about this fault code. What do you know? You know the blower motor comes on and off. You know you've got a blower motor problem. So let's look at how does this blower motor work, right? So this is from Autodata, which is a European information resource. I wouldn't necessarily recommend using it on North American cars often because it's oftentimes slightly different. And that is the case in this one. But I figured I would start there and look at all of my information resources. So in this circumstance, we have the blower motor is this M7 right in the center of the screen. We got four wires going to it. We've got a ground. We've got a power feed that's coming off of a high amperage fuse and a power feed coming off a low amperage fuse. And then we've got some kind of wire going to the AC control unit, which is A35 in the picture. What does that tell us? Generally speaking, in my experience, when I have seen a high amperage and a low amperage fuse going to the same thing, it tells me that that's some kind of a control unit. It has some kind of a brain or logic, and it may, in fact, have some form of ability to communicate. The low amperage fuse powers the module up, and the high amperage fuse carries the load that is being driven by that module, right? So looking at this diagram, I immediately said, well, it's probably got some kind of control signal that's, either a bus communication or a pulse width modulated or something of that nature. So then I went and looked at another diagram, and this is the lovely redrawn diagram because at the moment I was helping him, this is all I had access to besides the Autodata. So in this diagram, you might not be able to see, but we have three wires. We have a ground, we have a power, and we have a LIN bus wire. And so in this particular case, now this is the North American wiring, we've only got one wire for power feed, and that's a high amperage feed. So maybe in this particular circumstance, it's not working like maybe a CAN bus module where it has a high and a low amperage fuse. Instead, maybe it's just got a high amperage fuse, and that's it. So then I did actually get access to the Porsche wiring after the fact, and of course confirmed that everything I saw was correct, which is awesome. But with three wires, I knew we could still figure this out regardless of whether we had the OE wire or wiring. So both the aftermarket wiring and the OEM shows us there's at least one, maybe two power feeds to that blower motor, a ground, and some kind of control, right? So we know, what can we do? We don't care what this code is, right? Who cares what the code is? It's meaningless. It could have no code, and we don't care. Because at the end of the day, the only thing we really care about is the blower motor doesn't work right? So we just need to figure out, is the blower motor not working because it's failed internally? It has a power and ground issue, or is there a control problem? So what can we do? Well, we can monitor the powers and the grounds. We can back probe with, if you have multiple DVOMs, or maybe you've got a scope. Hopefully you've got a scope, because a scope is usually going to be your best answer for something like this, because again, we could put a 4-channel lab scope on this, right? We could go, hey, we're going to back probe the powers and the grounds. So if we got 2 powers, okay, we can cover that with a 4-channel scope and the communication wire. We can cover power and ground if it's just 1 and 1, and we can cover the control wire. And we can see if we're A, losing command, B, dropping power, C, losing a ground. We can see all of that with a scope in one shot. This is just an example I like to put in here just in case you're not familiar with PWM signals. Most of us are. But PWM signals, you can see the duty cycle is represented by on time. Now, I have seen where it's reversed from this. It's not common, but it does happen from time to time, where it's actually looking at the opposite. So 10 would be viewed as 90 instead of 10. So just keep that in mind in case you happen to run across that. A lot of the time, you can verify this with your scanner. You can look and see what the duty cycle command is, and you can look at the control wire if it's a PWM signal and see that the two match. So that's nice. What if it's a LIN bus controlled fan? LIN bus, if you've never worked on LIN bus before, it's a square wave signal. It's essentially just, it's not something you're going to be able to meaningfully interpret what's going on the waveform, unless you are really, really high level, at a level higher than I am for sure. I know there are guys who do, but certainly for LIN bus. But what we're basically looking for is a clean square wave, right? We want that clean square wave to be there whether the component is plugged in or not plugged in. If you unplug it, it should be good clean square wave. If you plug it in, it should stay the same. The waveform, as far as the pattern goes, the highs and low blocks might change, but the physical waveform still looks good quality, right? The signal quality is not affected by plugging in the potentially suspect module. So we could load test these powers and grounds going into this module as well. If that signal goes to flatline when you plug it in, then it's generally speaking, you'd be concerned that the module has got a problem internally. You treat it like any other module. You load test powers and grounds, and if those pass load testing, then you replace the module, which is the fan assembly in this particular case. We could also current ramp the fan, right? We could monitor the current going to the fan as the motor is running, and when it stops, if it glitches out, we could see what happens with the current, right? If the current is, if we're seeing big spikes high or dropouts low, where it's drawing no current at all, it's pretty reasonable to assume that if we're not losing power or ground, we got a problem internally to the motor. So multiple different ways we can check this. I just wanted to give an example of a LIN bus waveform, because I think a LIN bus waveform, if you've never seen one, it's good to know what you're looking for. Again, we're just looking at signal quality here, right? So we have good switching high and low. There's no crazy noise. There's no, it's not spiking super high or super low, nothing abnormal here. You'd want to look at your voltage levels and make sure that your voltage is normal as well, which I guess I cut off in this picture. Oops. But anyhow, typically speaking, you can find LIN bus waveforms almost anywhere, and there's so many cars with them now. If you don't have a known good, you can probably hook up to any car and grab one quick if you need to know what it needs to look like. Anyhow, they did power and ground load testing. The LIN bus did have a clean square wave after I directed them to check that, and it had no effect whether it was plugged in or unplugged. Now, they did look at the current ramp, and the current ramp was poor. So they had dropouts. There were also spikes. So you could see the motor was essentially starting and stopping, and there was internal resistance on the motor. That definitely does happen on a lot of DC motors, so really no surprise there. So anyhow, just like to prove here that the code is irrelevant to the diagnosis, right? We were able to figure out what was wrong with this without using any information related to the code. We just looked at the symptom only and said, all right, how does the system work? We can reasonably figure out how it works and determine what the root cause was without having to have really any service information for the most part, right? There really wasn't anything we need to worry about. You could also, I didn't mention, but if you had bidirectional control of the fan through the HVAC control head, you might have been able to do some additional actuation with the fan, actuating the speeds high and low, bypassing the switch portion of the equation to do some additional proving out whether or not it was a control issue. So this is the last case. This one here, this is a diesel. I did add this one back in just because I think it's got some good points if you don't work on diesel, right? If you work on diesel all the time, most of this, you're going to know exactly what's wrong, probably before I even get halfway through. But I think it's still another case that illustrates the central point of what we're talking about here in the class, right? Following the symptom, right? So the symptom was vehicle stalls, runs rough when it restarts. Sometimes it won't restart at all. So here's the fault code from the initial scan that the shop gave me. They shared this with me. So we have a ton of different codes here, a bunch of different stuff, airflow restriction, catalyst temperature sensor, injection timing performance, fuel injection quantity higher, etc. So they cleared them out. Only thing they got back, part by wire, was because it got unloaded off the tow truck and they hadn't actually set it back into its normal position. So disregard that. The only code that came back that was a, quote, permanent code was fuel injection quantity A higher than expected. So, like I said, disregard that first code. What do we have left? Just the one code. So let's go check and see, do we have any information from service info? Now, Chrysler, as a general statement, tends to be reasonably decent as far as what they give you. Now, they actually give you more and more the newer the vehicle. They've just been ramping up and improving as time has gone on. Their vehicles haven't gotten any better, but their service information certainly has. So they do give you a list of possible plausible things that could cause this fault code to trip. So we have quite a long list here. We have low pressure side related stuff. So the fuel pump inlet, strainer plugged. We got the fuel pump module, which would be the in-tank delivery, obviously being a problem. We could have a mechanical engine problem. We could have a fuel filter plugged. We could have a PCM failure. We could have air leaks. Yeah, I love how they always love to include PCM. Every OE fault chart in the planet says PCM is always in play, right? I can't remember reading one that was an engine fault code where that wasn't listed. I don't know. I think the OEs just like selling PCMs or ECMs, you know. So anyway, they give us a little more detail here. So talking about what they're doing, how they're monitoring it, what they're actually using to calculate and determine. So we see that the PCM is essentially looking at correction based off of what it's reading out from the oxygen sensors. So it's essentially, you know, just like closed loop fuel control. So it's just looking at it to determine, hey, how much excess of fuel are we really seeing here? What's going on, right? So now we need to figure out where we should go with this. So the fuel level on the gauge reads full. Cranking cadence sounds normal, so I didn't have any suspicion that we had a mechanical problem here. Everything seemed good. It wasn't spinning over ultra fast like it had low compression or anything like that. The vehicle would start, and it would run shortly, but then it would stall. I also noticed that if I let it sit longer, then it would start and run a little bit longer before it would stall. Fuel rail pressure, desired and actual, matched perfectly when it would start and when it ran initially. So I'm not suspicious of anything related to we don't have fuel in the tank and the gauge is off, or we've got an issue with, you know, mechanical driving of the high pressure pump or anything related to that. I'm not really suspicious of mechanical. I'm not really suspicious of fuel delivery being a problem here. So where are we going to go next? Now, if you're familiar with diesels, you know that contamination is a major, major, major problem. Common rail diesel, their biggest enemy is contamination. Now, this is a general service bulletin from Ford, so not a Chrysler, but I think it's important to remind yourself that common rail diesel is a common rail diesel. Doesn't matter whether it's on a big, huge semi-truck or whether we're dealing with a small consumer diesel. Common rail diesels are still victim to the same problems. They're still susceptible to the same issues, and they absolutely can still have some of the same failures. And fuel contamination is 100% a very common problem. So that was my feeling, was we've got fuel pressure here. We've got fuel delivery. We have what we should have in order to start this vehicle. I'm not suspicious of a mechanical problem. So I did not put the tree of possibilities in this particular slide set up here, but that is, I went down the same tree of possibilities and drew it up for myself and said, okay, let's knock off all the stuff we got here. The engine can breathe. The engine has compression. The engine has fuel delivery. All of the stuff it should need to start is there, but it doesn't sometimes. So I said, let's go look at fuel contamination. Also had an interview with the customer through the shop, and they mentioned filling up the vehicle not long before the stalling started, which was another clue that made me think, uh-oh, contamination. Now, this is something some of you may have seen before, and everyone's mic might be muted, but I'm sure you're all laughing, right? You'll notice how the diesel pump is black and the gasoline pump is green. In some places, the diesel pump is green, and a lot of people are apparently not in the practice of reading, and instead they pick up the green nozzle, which is exactly what I think happened in this situation. This guy actually moved up to the northern states from the south. I don't know if gas stations are different in the south than they are in the north as far as how the pumps are labeled or what might be the case. I had two parents who owned common rail diesel Jettas that got recalled, and the biggest fear I always had was that they were going to make this exact mistake. They did not, thank God, but I always slept in fear that they would. So anyhow, I told the shop, all right, let's pull the fuel filter housing off and let's take a sniff. I sniffed inside the filler neck and I thought I smelled gasoline. And I said, uh-oh, I'm pretty sure I smell gasoline. Let's be sure. So we pulled the fuel filter housing apart down on the bottom of the vehicle, and what came pouring out? Nothing but gasoline, almost exclusively gasoline. Then ran the in-tank pump repeatedly to discharge as much of the stuff that was in the tank as possible and found very little diesel. So the thing I wanted to get across with this case was, could we have solved this without any codes? I think the answer is yes. I think that the codes that we did have, or the only one that came back, was a reasonably helpful clue in this case, but it wasn't essential to solving the problem, right? I think familiarizing yourself with a common rail diesel and getting comfortable with the facts, especially that general service bulletin from Ford. Diesel is so, man, it's all about some really basic facts you need to get comfortable with and memorize. Clean, non-aerated fuel, not contaminated, is absolutely unequivocally crucial. The only diesels that really run well, and they won't run on aerated fuel, but they will run on gunky fuel, is the really old ones prior to common rails sometimes will start and run. If we're talking about vane pump systems, they're much more tolerant. Some of those you can get fuel contamination and they'll survive. But common rail diesels, generally speaking, they do not survive contamination, especially if you get gasoline in there. And the reason for that being is lubricity, right? Gasoline is not a lubricating substance the same way that diesel fuel is. When you put non-lubricating substances like ethanol containing gasoline, which we know ethanol is corrosive, that is going to cause major damage to common rail components. So I'd also like to say that with common rail, get yourself familiar with whatever OEM you happen to be the most familiar with common rail diesel. And then if you deal with any other common rail systems, you'll be comfortable, right? Because again, they're still using the same basic systems to do the job. They might do it a little bit differently, but a common rail is still a common rail at the end of the day. And being able to get yourself that tree of possibilities and understanding how a common rail diesel functions will allow you to work on those vehicles with comfortability and not with a lot of uncertainty and fear. So this is just the final notes and takeaways I have. Presence or absence of codes, specific codes, you don't want to get hung up on that, right? We don't want to think about it as, hey, we don't have timing faults, so it can't be timing, or we don't have misfire faults, so it can't be misfires. If you've worked on a Ford, you never want to take it on faith. If there's no misfires tripped, you could still have a misfire. The only way you can be sure is to prove it, right? So we never want to hang our hat on that fact. Codes or no codes, we want to follow that symptom. Now, if you only have a code and no symptoms, obviously we're going a little bit different route with that. But codes should be looked at as clues. The other thing we want to do is try to tap our service information for resources, but bear in mind that how much help you're going to get from your service information is going to vary widely. Now, if you are working on European vehicles and you do need additional information on how a system works, you can write into All Data or Identifix and send an information request. They do have access to the factory OEM websites. And in many cases, they will provide you with those training documents that might give more description of operation stuff if you ask them explicitly for them. So if you're working on a BMW and you say, I'm working on an E90 BMW, can you send me, hey, Identifix, send in a product support email and say, hey, Identifix, can you send me the E90 training manual and maybe the N52 engine training manual? And those documents can then be retrieved from BMW's website and emailed to you so that you will have more information and maybe have a better chance at understanding how the system works. Now, if you don't have those documents, or maybe Identifix or All Data fails to get them to you, contact me. I do have a lot of those documents, and I can try to help you if possible. I can't make any promises, but I will try to help you if I can. Drawing yourself the tree of possibilities, I encourage you to do this as much as possible. If anything else, number one, it'll help you figure out what the root cause of the symptom is, but it will also give you a better grasp on whether or not you fully understand how the engine works, right? And I like to say that European cars are in many respects like the real life ASE test, right? Because when they don't set a fault code that they should set, like a timing related fault, they're testing you. They're testing your knowledge of an internal combustion engine. They're trying to find out, do you really know that timing could affect how much air mass is being ingested into the motor? Well, if you know that, then you will examine that possibility, regardless of whether or not the control unit gives you a fault code to give you a clue. So again, I think that's the most crucial thing to take away is I would strongly recommend embracing that practice. I think it will help you a lot. And, if you want the ones that I've already drawn up, or you have suggestions or thoughts on any of them that you'd like to add, we can make it a collaborative thing, and I'm happy to do that. I'd love to make these available and help you out, because I think the more of this stuff you have, the less you have to lean on bugging your teammate next door in the stall or whatever. You can rely more on yourself, and you can hold yourself accountable to these questions without maybe having to ask other people. Not that you shouldn't, because collaboration is a tremendous tool. The other thing you want to remember is what fault codes are available for a given control unit. Now, your service information is the only thing that's really going to help you on this to let you know whether or not a fault code could or could not be triggered, right? So it's important to keep that in mind. It's also important to remind yourself that the scan tool may or may not produce codes that are deciphered correctly. You could even get incorrect fault codes from your scan tool. It might tell you that it's this code instead of this code. Now, we dealt with that a ton on European cars at Identifix, frequently when people were using Snap-on scan tools on European cars. They would get wrong fault codes, fundamentally incorrect fault codes. And that's huge because it can send you down the wrong path. Again, I think if you focus on the symptom and don't worry so much about the fault codes, that becomes less of an issue. Now, I would also advocate that you should have at least 2 different brands of scan tool because at the end of the day, you're going to be having situations where one tool is going to let you down and you're going to need a second one at a minimum. The other thing you want to keep in mind is that all control systems are limited, right? They're made and engineered by human beings. Human beings are imperfect. So are the systems that are being operated, right? All of these control units have imperfect control structures. They're trying to make it run perfect, but they're not perfect. They still make mistakes. They still decipher situations incorrectly. They still fail to trip codes when they should or set codes that they shouldn't. That's always something we need to remind ourselves of. And the testing that you perform as a diagnostic technician is what ultimately determines whether or not something is a root cause. The code is not the answer. The code is nothing more than a clue. So I just like to hit that point home because I know it's rare that anyone goes to training who doesn't already understand that. But if you're less experienced and maybe you're just learning this, it's important to remind yourself of that every time you're working on a car. So that's the summary of everything we talked about. I'd like to hear from you guys. If anybody has anything they want to talk about, you got a specific case maybe you experienced that you'd like to share. Maybe you've got a question about something. Anything at all that you want to collaborate or talk about, we've got a little bit of time left here if anyone wants to unmute and talk. Oh, no microphone. Well, you can certainly type your questions into the messages if you got. Otherwise, if you don't, I got another one. I could certainly give you one other thing. I did have a car actually the other day. It was a 2007 Ford Escape, so an older domestic vehicle. This vehicle, the shop calls me and says, "Hey, the customer called us and said they're bringing the vehicle in, and the car doesn't go, doesn't accelerate," is the description they were giving me. So they get the car in and they, yeah, right, brake switch. So they get. I think this was before throttle mitigation on Ford, at least when you press on the brake. But shop scans it. They call me. They go, "Hey, there's no whiteboard." Absolutely, good call. That's the same thing for the tree of possibilities. They had no fault codes at all. So needless to say, the shop was really, really, really frustrated and confused because again, they got hung up on the fact that there were no codes, but the car drove like crap, right? So I said, all right, go take another drive. Go for a drive, see if it'll set any faults. I also told them to do the key on engine off and the key on engine running self tests, which to me is literally one of the greatest inventions in the history of vehicles, right? Thank you, Ford. I wish every single manufacturer had that function. I'm not saying it saves you every time, but it damn well saves you some of the time, and it makes your life easier. Also gives you the ability to verify if you fix the car a lot easier sometimes. So they drove it, and I arrived at the shop, and they were on the test drive when I got there. And the vehicle, the technician calls me and goes, "Dude, I'm stuck at the stoplight across the street." And I'm like, "What?" And he goes, "Yeah, it's not moving." And I'm like, "So what does it feel like?" He goes, "Well, it revs up, but it doesn't move." I'm going, "Uh-oh, transmission problem," right? So anyhow, I go over there and I jump in the driver's seat and he pushes the vehicle, probably 500 yards or something. And boy, I felt bad for him because that looked like an unpleasant thing to do. But hey, I was there for diagnostic help. I was not there to push a vehicle. I don't need any extra exercise. I'm good. But anyway, so brought it in. And Ford, as a matter of fact, has a really awesome PID that you can look at. Gear ratio measured and gear ratio desired. And that is an unbelievable diagnostic tool for determining if you have a failed transmission. Kuba was in the class with me by ATG at Vision, and they talked about this exact PID for being able to determine if there's transmission slippage. It's incredible. And I totally had never put this together before. Now, that's my fault, right? I mean, every place I ever worked at, I was like, we just go, oh, you got, usually the thing would set a, hey, internal clutch position fault or whatever, P0730 or whatever it might be, implausible position, etc., whatever. Some different code indicating slippage, and it matched the symptoms, so we just said, put a transmission in it, right? Now, I learned in the class that's not necessarily a guarantee, so you need to do a little more testing. So anyhow, I took it for a drive in the parking lot in case it stopped moving again, because you could turn it off, turn it back on, and it would move again temporarily. But you could monitor the gear ratio desired and the gear ratio measured, and you could see the gear ratio desired was like 2.89 for first gear, and the measured gear ratio was like 3.99. Now, if it's higher than what's desired, that means you have slipping clutch. But you have to ask yourself, is that because of pressure application issues via the valve body or solenoid function, or is that just a mechanical failure, right? So I went through, and sometimes you can put the vehicle into default line pressure mode by putting it in like a sport mode, or you can put it into like the low gears, like the gear 1 or 2 or L. Sometimes that will bump the pressures up. And so I did that, and I looked, and I could see the line pressure and all the solenoid pressures get jacked up. That should allow the vehicle to shift if it's a pressure-related issue, right? No change whatsoever. Gear ratio desired and gear ratio measured was still way off. 3.99, 2.89. So, of course, that tells us, yes, we have a major internal slippage problem. So I concluded, yes, we need a transmission. The shop was just mystified that there were no fault codes. And I'll admit, with that level of slippage, I was pretty surprised that there was no fault code trip at all. But again, just another great case that illustrates the point that we have absolutely cannot sell ourselves on, hey, it has a code, it doesn't have a code, so it can't be blank, right? Never ever stand on that. So just yet another case. So I feel like now after I've written this class, now I keep seeing this over and over. So maybe it's like once you see it, then you see it all the time. Maybe that's what it is. Maybe that's why I'm always thinking timing, right? Because I took a ton of calls on Volkswagen Audi, and it was always timing. Maybe not always, but a lot of the time, right? So anyhow, if anyone has any other questions or anything else they want to give feedback on, if you have suggestions, you have thoughts, anything you'd like to share, feel free to message me on Facebook. Feel free to, give me suggestions. If you have other stuff you'd like to see a class on, now that I work for Top Down and I'm going to be building classes, I'd love to hear what kind of stuff you guys would like to see classes on. If you live in Minnesota or in the Midwest area, I may teach some of these classes locally as well. So certainly if there's anything like that you think of that you'd like to, see more on. The other thing that I do have that's kind of a unique thing is I have the ability to take my time on a lot of these diagnoses because I'm not doing mobile as make a living, right? So I can spend time developing new testing techniques. I can try things on cars that a lot of other folks don't have the time to do. There you go. Chad has a question on Jaguar gear selectors. Adrian, that's your wheelhouse. You're probably the best guy to answer that one. Oh man. But stuff like that, I have the ability to take the time, and I can spend 6 hours at a shop because most of the shops I have relationships with, they don't care how long it takes me to fix something. They're just like, yeah, do whatever you do and come tell us when you have an answer, and they leave me to do my thing. And they even let me bug their technicians to take stuff apart because I don't do any disassembly. If the body panel's coming off, I call someone over. I'm like, I'm not breaking it. You break it. So anyway, yeah, there you go. Proximity to the cup holder. Yeah, that sounds about right. Oops, someone spilled on it, right? Oh, man. Oh, for the classics for Porsche. As a matter of fact, I have a lot of Porsche training documents I'm uploading to my Google Drive. So out of print stuff that you can't get anymore. So I'll definitely try to help you with that for sure. But yeah, just message me if there's anything you're looking for. And if I have it, I'll try to help you with it for sure. But I know that Identifix does have a number of old books too. So if it's not digital service information, they do actually have physical printed books in some situations. So it is, it's definitely something that you'll run across. If you get an older vehicle, send an information request in, especially to Identifix. So they will try to help you if they can. So yeah, if you guys don't have any other questions or anything else you want to talk about, we'll go ahead and we'll wrap her up, and I'll end the recording here. I greatly appreciate everybody coming. So thanks again for participating and coming to this class.